slides the fates of pyruvate. Right? You can go on aerobic metabolism, or it can get fermented in anaerobic metabolism in different ways. But if we look at the top part of the pathway, right? So here's glycolysis coming down here. Although it's kind of starting from here, here's glucose, right? So it's kind of going this way. Here's hexokinase, right? This is the phosphohexosaisomerase here, right? Short phosphofructokinase and aldolase here. Okay. So that's what we've seen so far, right? But clearly the cell is, many cells are able to take up sugars or store sugars in many different ways. And the cell wants to be able to mobilize all of that for energy. It's obviously not going to want to throw away sugar because it's not glucose. So it's highly unsurprising that there would be enzymes around that interconvert other sugars to glucose. Right? It's also not surprising that cells want to store glucose in a way that allows it to be available at some later point when there's not so much in the environment. And so cells use glycogen for that. And so glycogen is here, and it can get broken down in a couple of different ways, which we'll talk about. We also have these, here we've got larger sugars, dipeptides. There are specific enzymes that break those down. Right? There's a special pathway for galactose. There's another special pathway for mannose. You see it sort of comes in at different points here. Right? And if we get to fructose, right, there's multiple pathways for that. So let's kind of just look a little bit at some of this. We're not going to go into detail on any of these reactions, like in the way of mechanisms, but it's kind of good to get a sense of, you know, what some of the forest around the glycolytic pathway starts to look like. Right? You can download these gigantic metabolic maps online, which show, you can put it up on your wall if you like that kind of thing. And they've got thousands of reactions illustrated. We're only covering the simple ones, but we can look at least a little bit on some of the other ones. So structures of starch and glycogen. These are the storage polysaccharides. You saw them last time. Glycogen is broken down from the reducing ends. From the non-reducing ends. So enzymatic removal from entry of monomers into glycolysis is from the non-reducing end. So the reducing end has a free anomeric carbon capable of being oxidized. So in these reactions that reduce copper. So when the cell breaks down glycogen, it does so by means of a phosphorylation reaction. So we saw glycogen phosphorylase, at least briefly. We encountered it as an example of an enzyme that is regulated by phosphorylation. And we had glycogen phosphorylase, which is itself phosphorylated by kinases, and then a dephosphorylated form. And the two forms have different levels of activity on glycogen. But the reaction it catalyzes is a phosphorylasis, which is like a hydrolysis, except instead of water, it's a phosphate, inorganic phosphate that does the attack. Right? So the phosphorylasis reaction results in glycogen with one glucose removed and glucose 1-phosphate. Right? So this is inside a cell, right? And so the cell, because maybe it doesn't have much glucose coming in from the environment, has decided that, or maybe it's getting ready to divide, it really needs to maximize its store of high energy trinucleotides. It's going to mobilize its glycogen to generate glucose so it can speed it through glycolysis and the other pathways and make a lot of ATP, something like that. Right? So when it's inside the cell, it's doing this by a phosphorylase reaction. Okay. And the phosphorylase reaction, by glycogen phosphorylase, doing a phosphorylasis reaction, generating a compound that is itself now phosphorylated, right? So since it's phosphorylated, it's easily interconverted by a mutase to form glucose 6-phosphate. And this mutase should be familiar. That's the enzyme we used to illustrate bioenergetics. That's the one for which KEQ equals 19 in favor of G6P over G1P, because G6P is lower energy than G1P because G1P has an acyl phosphate and G6P doesn't. Okay. So now we don't have to invest this ATP, right? So we talked about glycolysis, like we're coming from here, and the first step is investing ATP. But if we come from inside the cell, we actually don't have to invest the ATP. So if we take in, sugars in the diet, starches, and then it gets processed through the alimentary canal, and you look at the enzymes that break it down. The enzymes that break it down is amylase, right, to form glucose. Obviously, this is the enzyme in saliva. That's why if you hold a cracker in your mouth, it gets sweet after a while because it's breaking down the starch to free sugars, like this. And this enzyme operates by hydrolysis, right? So this glucose is then in your alimentary tract and it gets absorbed into cells, right? But then, of course, the cells have to invest this ATP. So why is that? Why doesn't amylase also work by a phosphorylasis reaction, since it would save the cell in ATP?
Can't move through the membrane.
Can't get through the membrane. That's right. So if you had glucose 1-phosphate here already because amylase did this, then you couldn't get the phosphorylated compound couldn't make it in through the membrane. So it doesn't really have that option. I suppose you could imagine that they could have evolved a specific transporter for this phosphorylated compound that would take it and bring it into the cells. But that's just not the way it works.
That transporter would take an ATP probably?
Yeah, it would take energy to make the transporter, insert it into the membrane, and then maybe to drive the transport, but it might also take energy. Because moving in the negatively charged phosphate. Plus you might have a charge balance issue as well. Not sure about that, but yeah. Anyway, the distinction that's important is hydrolysis versus phosphorylasis, and why one happens inside the cell by breaking down glucose, and the other one happens by amylase in the diet, basically. Okay. And then you should be aware of this enzyme that interconverts G1P and G6P. So that's one aspect of these reactions. Another aspect of these reactions is the specific enzymes, as I mentioned, these guys up here, to convert disaccharides to monosaccharides. And then we have these kind of other details here. So if we have sucrose in the diet, it gets cleaved by a specific enzyme to make glucose and fructose. Glucose, of course, goes by way of hexokinase. But if we have fructose, there's actually two pathways. One is a different version of hexokinase that simply phosphorylates it to generate fructose 6-phosphate. Now we're one step down the pathway. Right? We've bypassed this phosphohexose isomerase, because we already started with fructose. The other reaction is to, instead of investing the ATP here, it gets invested here to make fructose 1-phosphate. Right? There's an aldolase that cleaves this, right, to make glyceraldehyde and dihydroxyacetone phosphate. This is the same product that's made from our friend the aldolase in the straight pathway. Right? But this guy, glyceraldehyde, is not phosphorylated, so he has to get phosphorylated by another enzyme to make G3P, so that these two compounds can then be interconverted by TIM, and the G3P can go forward. Right? So this is, if nothing else, kind of an interesting kind of sidelight. If you kind of write it out and look at it, can compare it to the straight pathway. It gives you a sense of possibility of alternatives, and that may help you remember the reactions and just kind of cement what you know about how these things are getting interconverted. Because you've kind of basically done, by going through fructose, you've already got fructose 6-phosphate in the pathway. You've basically gotten through the first part of glycolysis by kind of a different way. But you're still getting to the same place. Right? Yeah?
Do you know what the overall return is the same?
I'm sorry, what?
Do you know what the overall return energy that you get by using fructose instead of glucose is the same?
It should be about the same, because there's no difference in the ATPs that have to be invested. Fructose is, I guess it could be directly in the food you're eating.